Hello, everyone. Good morning, good afternoon, good evening, depending on where you're listening to this session. My name is Mukesh Gupta, and in today's session, NVMe over TCP in the enterprise, I'll talk about a new end-to-end paradigm for storage connectivity between endpoints based on NVMeoF fabric standards. About myself, I'm a distinguished member of technical staff at Dell EMC and associated with the storage industry for more than 20 years. In today's presentation, I am being joined by Murali Rajagopal from VMware to discuss host-side changes for this new paradigm and NVMeoF fabric support in general. Hello, Murali, how are you?
Good. Thanks, Mukesh. Hello, everyone. I'm Murali Rajagopal, Director of Technology at VMware. A bit on my background. This is my 11th year at VMware, and I've been associated with the storage industry for the last 25 years.
Okay, thank you, Murali. In the agenda for this session, I will go over the market drivers and customer challenges that our customer face as a reason or motivation for coming up with this new paradigm for storage connectivity. I'll go over the terminology and evolution of NVMe and NVMeoF fabrics before describing this new ecosystem. Then we will delve into the components of this new ecosystem, and in the end, we close out the presentation with key takeaways. So without further ado, let's get into the presentation. Market driver and customer challenges. Customers have been continuously adopting NVMe all-flash arrays for their sheer speed and performance to leverage them for a variety of applications. With the rapid integration of 25 gig and 100 gig Ethernet connectivity in data centers, it's possible to bring this performance for remote workloads. The market shift towards disaggregation and composability get a boost with these high-speed interconnects to provide the cost and availability benefits from various software-defined storage implementations. Finally, the continued growth of SDS implementation, especially at the edge, points to the preference for simpler and cost-effective storage connectivity solutions. From the customer perspective, any storage connectivity solution should not only be able to meet the demands of today's workloads, but also prepare for the foreseeable future. The solution should be simple, cost-effective, and standards-based. In addition, the cost-effective connectivity solution should provide both CapEx and OpEx savings. Now, for the last 5 years or so, or maybe a little bit longer, a lot of enterprise customers are moving away from SCSI and going to NVMe for their storage connectivity needs because they see the potential to get better performance from such a shift. With its multi-queue architecture and simplified stack compared to the traditional SCSI, NVMe is poised to provide higher throughput and lower latency for applications natively running on the storage system. Traditionally, applications running on a host access external array-based storage with SCSI using either Fiber Channel or iSCSI. Even though NVMe SSD improved the storage array performance, but using SCSI-based protocol for remote access can add significant latency on the host applications. On the other hand, using NVMeoF fabrics, whether it's over Ethernet or Fiber Channel, can provide lower latency. Between the various NVMeoF fabrics transports, we believe that enterprise customers will gravitate towards Ethernet fabric, specifically towards NVMe TCP, because of the following reasons. Ethernet provides standards-based, high-speed, low-cost block storage access. If you look at 25 gig Ethernet, it's effectively provide the same speed as 32 gig Fiber Channel at a fraction of cost in terms of both dollar per port or dollar per gigabyte of bandwidth. On both of those metrics, Ethernet provides better economics that results in substantial upfront CapEx savings compared to Fiber Channel. Comparing NVMe TCP with other NVMeoF fabrics, comparing NVMe TCP with other NVMe over Ethernet transports, such as Rocky V2, TCP IP is ubiquitous and just works by default. It does not need any DCBX or lossless Ethernet requirements, nor any specialized configuration needed. Even though Rocky V2 will be desirable in some environment because of lower latency requirements, but the realistic end-to-end performance of NVMe TCP is similar to NVMe Rocky, especially considering the latency associated of the storage stack on both the host endpoints and also on the storage array. As offload emerge for NVMe TCP, the performance of NVMe TCP is only getting better. Finally, NVMe TCP is a better fit for edge use cases in comparison to other NVMe over Ethernet cohorts because of its lower complexity and cost effectiveness. Having said that, what the benefits of NVMe TCP are, NVMe TCP does face some challenges, specifically NVMe over discovery, NVMe over fabrics discovery problem. This discovery problem, specific to IP-based fabrics, can result in the need for host admin to configure each host to access at the appropriate NVMe subsystems. In addition, anytime an NVMe subsystem is added or removed, the host admin needs to update the impacted host. This process of explicitly updating the host anytime a change is made does not scale when more than a few hosts and NVMe subsystem interfaces are being used. Due to endpoint-centric nature of this process, it adds complexity when trying to use this process in NVMe fabric environment that requires a high degree of automation. If we compare this with fiber channel, the fiber channel faces no such discovery challenges as it has centralized services such as naming services, zoning services, and registered state change notifications or RSCNs. To this end, Dell Technologies is driving the industry ecosystem around NVMe TCP through NVMe Standards Committee to fill the gap around automated discovery of host and storage endpoints and provide a network-centric model that provide centralized services. With this background, let me introduce next-gen NVMe IPSAN, which is intended to be open, standard-based, and supporting connectivity from any vendor that supplies standard compliant components. Hence, we have made every effort to push as much of the required functionality as possible into the technical proposals shown in the previous slide. If you look at next-gen NVMe IPSAN, there are three major components involved. First, there are endpoints, which are either hosts or storage systems. For example, ESXi host or Dell EMC PowerStore storage array. And these subsystems and these endpoints, specifically, the storage endpoint, have a subsystems, NVMe subsystems defined on top of it. The second component for NVMe IPSAN is an IP network, which can be provided by any vendor. It can be used, or a Dell PowerSwitch can be used for this purpose. Finally, the CDC, or the centralized discovery controller, right, is the piece that's the glue in NVMe IPSAN. It's a controller for NVMe TCP endpoints. This CDC enables standard-spaced automatic discovery of itself by NVMe TCP endpoints in the NVMe SAN. CDC aggregates the information for the endpoints, provide access control, and generate fabric events to report the changes. The main functions of the CDC, and as you can see on the right, is no surprise that the main function of the CDC are alike fiber channel or similar to fiber channel, because what it intends to do is provide these functions which allows you to do automatic configuration similar to what fiber channel does. So various functions, CDC functions are, there's a discovery service. So as we said, the NVMe TCP endpoints are dynamically discover the CDC instance. It can listen and respond to those MDNS queries that are coming from the endpoint of the fabric. The endpoint registration service, it's the various endpoints, NVMe TCP endpoint, which is host again or subsystem, they can register their information with the CDC or centralized discovery control. The endpoint query service, with using that, the host of their subsystems can query this information about other endpoints through the CDC. So this essentially, provides the same functionality what you get from a fiber channel name server database. On top of that, there's a zoning service. So once the CDC have all the information from all the endpoints, orchestrator or an administrator can configure the zoning on with this information, and that zoning information can be given to the endpoints. And this information is given to the endpoint using asynchronous notifications, such that every endpoint knows now that a zoning either is changed, some endpoints are added, some subsequent added or removed in an automated way. So let's look at what Dell Technologies is doing on the NVMe IPSAN and its ecosystem. Dell Technologies, including VMware, have all the required components needed to build NVMe IPSAN. Specifically, it has endpoints, both hosts and storage arrays, switches, and NVMe IPSAN software, which is nothing but a CDC implementation, a centralized discovery controller implementation. Additionally, network automation services, which is optional component, but it can provide complementary support for network automation of underlying Ethernet fabric. So let's look at these NVMe IPSAN operations in a little bit more detail. In the first step, the network automation services can configure VLANs, create the network such that various endpoints and CDC can talk to each other from the IP perspective. Then, once this network is created, the server and the storage arrays can discover the NVMe controller automatically. After this, servers and storage service can discover the NVMe controller, the endpoints can register the information like NQN with the NVMe controller. Once all the information is with the NVMe IPSAN software, the CDC, operators or orchestrators can read this information from the database and set up appropriate access point or zoning changes. So once that zoning changes are made, this information is distributed, or it's sent using asynchronous notifications to these endpoints, and it reports to them that there's some changes happened. So based on that, the host or the servers can now connect to the storage array and start transmitting the data, making this process automated and scalable. As the number of hosts or subsystems grows, then this process is automated and provide the benefit or ease of use that this NVMe IPSAN is supposed to. The NVMe IPSAN solution from Dell Technologies provide a viable and cost-effective Ethernet-based alternative to fiber channel based on performance, better economics, simplicity, and automation. Now, when we looked at how this NVMe IPSAN components, three main components interact with each other, let's delve into this major components one by one. First, let's look at Dell EMC NVMe IPSAN software. As I mentioned before, it's a standard-based centralized discovery controller implementation from Dell Technologies for NVMe TCP hosts and storage subsystems. It can be provided, this software can be provided on top of the rack switches or any other switches, or it can be provided in a VM, for example. But it allows end-to-end automated support and integrated NVMeoF SAN fabric. This software can help reduce user configuration, ease of management for the end user, and provide a central repository, as we discussed before, for providing the name and zoning services. The main point is to provide network-centric automated management for Ethernet customers. And it's not surprising that all of these functionalities that it supports is similar to fiber channel. At this point, I would like to pass the control to Murali Rajagopal from VMware, Dell EMC's design partner for next-gen NVMe IPSAN, to talk about the host set changes.
Thank you, Mukesh. So before I start, a disclaimer. We are going to talk about the current support as well as the future support, but there are no commitments from VMware because future supports are always into changing priorities within the company. This is a disclaimer. Okay, VMware has had support for both fiber channel and RDMA and NVMe fabric transports since vSphere 7.0 release. In vSphere 7.0 U3 release, we plan to add support for TCP transport. VMware has been working with partners to support their external storage with all NVMe transports. In this presentation, we'll, however, focus on NVMe TCP transport with Dell EMC arrays. This chart shows the ESXi storage stack as of 7.0 U3. The VMware storage stack is architected to support many storage technologies and protocols, including SCSI and NVMe. The stack diagram is highly simplified to show the main layers. Boxes colored in blue indicate SCSI, while the boxes in green indicate NVMe. Gray boxes are protocol agnostic. There are 5 main layers, and starting at the top, the virtual machine monitor or VMM layer faces the guest operating system, presenting a virtual SCSI or virtual NVMe storage interface. Below the VMM layer is the virtual SCSI and NVMe layer, which enables a front-end I/O path or a back-end I/O path, for example, for raw device mapping devices. Below this is the file system layer, where we have support for VMFS, NFS, vSAN, etc. I/O simply writes as read or write commands at this layer. Below the file system is the core storage layer, also called as pluggable storage adapter layer or PSA, which deals primarily with multipathing. Top of this layer assumes a SCSI format. The diagram shows a dual stack, SCSI on the left and partially NVMe on the right. Both SCSI and NVMe adapters are supported. A key component is the NVMe High Performance Plugin or HPP that replaces the SCSI native multipath plugin or NMP. HPP optimizes I/O with wider lanes and lockless behavior, ideal for NVMe protocol. Lastly, we have the driver layer, where storage drivers such as Fiber Channel, iSCSI, and NVMe reside. Also, we have NVMe drivers for local PCIe attach and Fabric drivers for Fiber Channel, RDMA, and TCP transports. We have support for both active-active as well as NVMe asynchronous namespace access, or ANA for short, both key support for our NVMe transport. Next, our projected future stack is shown in the diagram. Notable changes from the previous chart are at the right side of the core stack, which is now 100% NVMe. No SCSI conversion whatsoever. This enables a true end-to-end NVMe experience, starting at the guest and all the way down to the NVMe device driver layer. The stack will also be optimized for high performance with high IOPS and minimum latency, quite suitable for NVMeoF fabrics. A number of feature enhancements are expected to be added over multiple releases, which I'll describe next. In vSphere's releases 7.0 to 7.0 U2, we have the basic support for NVMeoF fabrics, including all flavors of namespace IDs, multipathing, compare and write fused operation required for proper working of VMFS and NVMe discovery. In 7.0 U3, we're planning to add support for NVMe TCP transport, abort enhancements required by VMware to deal with scaling and performance. We are also planning to add support for central discovery controller. Moving on to the future, the outlook, we plan to add support for many features, including virtual volumes with NVMe, end-to-end NVMe, reservations, metro cluster, auto discovery of discovery controllers, in-band authentication, copy across namespaces, boot, and many other features. In particular, I want to draw your attention to the features most relevant to TCP transport shown in the diagram in the oval boxes. Features such as mechanisms for NVMe discovery, in-band authentication, among others. In summary, VMware is proactively working towards enhancing support for NVMe technology and working with all our partners to enable the NVMe ecosystem. Now back to you, Mukesh.
Thank you, Murali. Finally, let's talk about Dell EMC PowerStore storage system, which provides support for NVMe TCP target and works with Dell EMC NVMe IPSAN software or CDC to complete the full ecosystem for next generation NVMe IPSAN. Dell EMC PowerStore is an active NVMe scale up and scale out next generation container-based storage system. As you can see in the picture, PowerStore is a cluster composed of many appliances. Each appliance has 2 nodes, and storage that's given to an appliance is native to that appliance. That means it's not shared with other appliances. Both the nodes in a single appliance are able to share the storage. With PowerStore, earlier this year provided the support for NVMeoF and will provide the NVMe TCP support soon. In terms of features that are present, that will present in NVMe TCP support for Dell EMC PowerStore, will be NVMeoF Fabric specs compliant with version 1.4. Will support the enhanced discovery, specifically as also known as Technical Proposal 8002, with persistent connections to the direct discovery controller and async notifications. We provide best effort about command processing, data and header digest support. As Murali also mentioned, we have a support for ANA or asymmetric namespace access and multipathing support with the async ANA group change notifications. We support NVMe reservations and many other features, including the CDC integration, which is the key to the NVMe IPSAN. Going in the future, we'll be specifically again about dispersed namespaces for metro clusters, NVMeoF Fabric in-band authentication, and NVMe copy commands. Now, with that, we have reached the end of this presentation. Here are the key takeaways from this session. NVMe TCP is uniquely positioned to become the de facto choice for a SAN. Next generation NVMe IPSAN is a standards-based, as we have seen, fast, simple, and cost-effective Ethernet-based alternative to fiber channel SAN. And finally, Dell Technologies and VMware are working together to bring NVMe TCP innovation and solutions to the industry. Thank you very much for joining the session.